cooling, it is a differential equation that describes the rate of change of an object's temperature and realizes that it is proportional to the object's temperature and the difference between it and the environmental temperature. So this is the differential equation we're looking at here. So dt dt, that's the rate of change of the temperature. And it says that the rate of change of the temperature is proportional to the object's temperature and the environmental temperature. So there's some difference here. And if you think about, well, what happens if you take a warm bowl of soup and you put it out in the winter? So if this is warm and you put it out in winter and this is cold and this is some positive number, and so we need this negative sign here because we know that the rate of change of that soup would be negative, meaning it's going to be decreasing over time. However, if we take something cold like an ice cream cone and we take it out in the summer, if this is smaller than this, and this is going to be a negative, and so the negative and the negative make it so dt dt is positive, because we know what happens if we take ice cream out in the summer, it's going to warm, versus a bowl of soup in winter, it's going to get cold. Okay, and then what's this K? Well, K is some constant affected by the object's specific heat and its exposed surface area. So different things are going to cool at a different rate based on basically the chemistry of that object, and then of course the exposed surface area. So whether it's insulated or not, how much of the surface is touching, things like that. Okay, so we get this differential equation, and it happens to be a separable differential equation. We can separate the variables, or the capital T, which is temperature as a function of time, and then little t, which is just time. TE is some constant, that's the temperature of the environment, and K is of course some constant. So when we separate, then we integrate, and then we find C, and we know that when little t equals 0, capital T equals T naught, that's just saying that we're defining the temperature of the object at the start as T naught. That allows us to find capital C. We can take capital C and we can plug it back into the equation, and then we get this guy. Then we want to solve for capital T. And so what I end up doing is I exponentiate to get this, and then I have these absolute values and I have to make some decisions. And so I think, okay, what are the two cases? Well, T naught can be greater than TE. In that scenario, both the absolute values are positive, thus I can just drop them. And if T naught is less than TE, then they're actually both negative, and the two negatives would cancel. So in either way, I get this same equation, and I add TE to the other side, and I'm looking at this. There is the temperature of an object as a function of time based on Newton's law of cooling. And let's just check our answer. What happens to that when little t equals 0? Well, we better get capital T equals T naught. And so when you plug in 0 for t, this is a 1. The TE and the minus TE cancel, and you're left with capital T equals T naught. Whew, that's what it has to be. That's where we defined it. What happens when t goes to infinity? Well, if you let the bowl of soup sit out there long enough, the bowl of soup is going to become the temperature of the environment. So we know that if we let t go to infinity, capital T has to go to TE. And that's also what happens here, because when you let this guy go to, when you let little t go to infinity, this is a negative exponential. This just goes to 0. 0 times this is 0, and you get t equals TE, which we know to be true. So the equation makes sense based on how we've done things. And then if you look at the graphs of these two different scenarios, this is the bowl of soup graph right up here. This is the top one. Take a bowl of soup with T naught greater than the environment, and it's going to cool off to the environment. This is our ice cream down here. Put some ice cream outside, and it's going to warm up to the environment. Okay, so both of these things make sense. Again, if T naught is bigger than TE, then this is a positive. So it's a positive decay, and so you end up taking TE and you keep adding something smaller and smaller and smaller. So at the beginning you add a lot, and then you add less and less and less, so it's actually going to go down. And then when this is smaller, this is a negative, and you add less and less of a negative, but adding less and less of a negative actually increases your value, and then you go up. And both of these asymptotically approach the environmental temperature, meaning if you let a bowl of soup or ice cream out long enough, both of them will slowly reach the temperature of the environment. I really like this question. It's just another example of how a differential equation describes things that happen in nature. But this is kind of more of a chemistry example, and this happens to be Newton's law of cooling.